Hello friends, today we will be continuing dynamic programming. Now in this lecture we will be discussing a solution using dynamic programming for the multistage graph problem. So what are multistage graphs? A multistage graph is a directed graph represented as G is equal to VE in which vertices are partitioned into k greater than 2 disjoint sets. So we have a graph which has whose vertices are partitioned into k greater than or equal to 2 disjoint sets, and there are some properties in this graph as well. Now if there is an edge u comma v which belongs to the edge set, then it means that this node u belongs to one stage and this node v belongs to the immediately next stage. That is what is meant by if u belongs to, let's suppose, v of I, then v belongs to v of I plus 1 for some I from 1 to k. Now another property of this multistage graph is that the sets, the first set and the last set, both have a single node, node 1 in v1 stage 1 and node n in the last stage vk. The first vertex in the first stage, the lone vertex rather in the first stage, is known as the source, and the vertex and lone vertex in the last stage is known as the sink, and they are represented by S and T respectively. Now we also have costs associated to each edge in the graph, and we represent that cost array as C of I comma j. That means C of I comma j here means the cost of the edge from I to j. Now the cost of a path from this node source, the lone node in the source, to T, that is the lone node in the last stage, is the sum of the costs of all edges in the path. If you look at this example here, if we start from node number 1 and want to go to node number 10, let's suppose, obviously there are so many paths over there, and let's take an example of the first of the path from node 1, then to node 2, then to node 5, then to node 8, and finally to node 10. This is a simple path from from source S to the sink T, from the first stage to the last stage, and the cost of this path would simply be the sum of the costs of each of these edges in this path. That is sum of the cost of edge 1 to 2, sum of the cost of edge from 2 to 5, similarly cost of plus the cost of edge 5 to 6 and 5 to 8, sorry, and then add the cost of edge 8 to 10. So this is a simple representation of multistage graphs. Now we try to find some solutions to the multistage graph problem. But what is this multistage graph problem at the first hand? The multistage graph problem is to find a minimum cost path from S to T. So we have a multistage graph, and our challenge or the problem here is to find the cost or the minimum cost path from the first stage to the last stage. Obviously there could be many paths, but we have to choose at least one. The conditions that we need to consider here are that every path from this source to sink or from S to T has to start from the first stage, obviously, get to the next stage, that is stage 2, then go to stage number 3 and so on, and finally terminate in the last stage, that is stage or stage K. Now if we look at this problem of trying to find a path in a multistage graph from the first node to the last node, or from first stage to the last stage, now we can observe that we need to make only k minus 2 decisions, where k obviously is the number of stages. In this example that is shown here, we have k is equal to 5 stages. At the bottom you can see v1, v2, v3, v4 and v5. These are a total of 5 stages. We have one node in stage 1 and one node in stage k, that is 10. So if we want to find a path from the first node in stage 1 to the last node, or the node in stage k, obviously we need to take only k minus 2 decisions. Now let's have a look. Now let's suppose if we are at stage K, how many decisions do we need to make in order to get to this T or the sink? There is no decision to make because there is only one node in the stage. Similarly, if we go back one stage, means in stage number 4, let's suppose we have chosen node number 8 here to be on the path. Now once we are at node 8, do we need to make any decision to get to node 10 in the final stage? There is only one edge from that particular node to the last node, so there is no decision to be made. There is simply we only need to select the final edge. Similarly, if we have chosen node number 9 in this k minus 1 stage, in the 4th stage in our example, we don't need to make any decision because there is a single edge from this node to the sink. But however, if we are at stage, let's suppose stage number 3 in our example, or k minus 2, if we choose, let's suppose node number 5 in our example here, do we need to make any decisions which path to follow? Obviously yes, we have two edges from node number 5, one leading to node number 8 and another one leading to node number 9. So we need to decide which path to follow from 5 if we have chosen 5. Similarly, if we have chosen 6 in this stage to be on the path, the next decision would be whether to choose node number 8 or node number 9. Similarly, the same thing applies to node number 7. Similarly, if we go one stage backwards in stage number 2 in our example, if we have chosen 2 to be on the path, then we have to make again two decisions, whether to choose 5 in the next stage or whether to choose 7 in the next stage. Similarly, if we select, for example, node number 3 in the second stage to be the node on the path, we need to make 3 decisions, or we need to make we have 3 choices to be followed. Either we need to select node number 5 in the next stage, or node number 6 in the next stage, or node number 7 in the next stage. Now obviously the choice has to be such that the cost is minimized. So we need to make decisions only in stage number 3 in our example, stage number 2 and stage number 1. So if we see, we have a total of k stages. K is equal to 5, 5 minus 2 is equal to 3. That is why we said that a dynamic formulation for a k stage graph problem is obtained by noticing that every S to T path, source to sink path, is a result of the sequence of k minus 2 decisions. Okay, so that is why we said k minus 2 decisions. Now the ith decision, or when we are at stage number I, this decision involves determining which vertex in the next stage, I plus 1th stage, where I ranges from 1 to k minus 2, is to be on the path. So obviously you can see in our example, let's suppose, as I said, we are at stage number 1. Okay, we have chosen node number 1. Which particular node in the next stage has to be chosen such that the path we select has the minimum cost? And these decisions have to be made only for k minus 2 stages. So let's try to formulate a solution for this multi-stage graph problem using dynamic programming. Now let P of I comma j be a minimum cost path from vertex j in Vi in stage I to vertex T, to the final vertex. So we are in some stage I and we are choosing some node j in that particular stage I to go to vertex number T. So P of I comma j be the minimum cost path from vertex j in Vi, means stage I, to vertex T, the final vertex in the last stage. So we are selecting node number j in stage I to go to vertex number T. Similarly, let cost of I comma j be the cost of that path. So we are representing our path in the form of P of I comma j, where, for example, I represents the stage and j represents the node in that particular stage that we have chosen to be on the path. Similarly, cost of I comma j will store the cost of selecting node number j in stage I to go to vertex T. Now the recurrence is formulated as cost of I comma j is equal to the minimum of the cost of the edge from node number j to some other node in the next stage plus the cost the cost that has been computed using the same recurrence, and we need to decide which particular edge needs to be selected, or we can say which particular node in the next stage needs to be selected so that we have the minimum cost path to t. So this cost of I comma j here representing minimum of C of j comma L. C of j comma L is the cost of the edge j comma L. So let's suppose our edge that our node that we have selected, j is 3 and I is 2, meaning the second stage, vertex number 3. We are there, and we need to have to choose whether we will select node number 5 in the next stage, or we'll select node number 6 in the next stage, or node number 7 in the next stage. So we need to make a decision. We want to select the minimum, that node which will lead to the minimum cost. That is what that recurrence basically means there. It means that if we have chosen node number 3 in stage number 2, okay, we need to choose one of the nodes from 5, 6 or 7 such that the final cost is minimized. So how do we compute that cost? If we select node number 5 in the next stage from node number 3 in the previous stage, the cost of the edge here is, let's suppose it is 1. Okay. Similarly, the cost of the edge from 3 to 6 is 2. Similarly, the cost of the edge from 3 to 7 is 2. Okay. So we add the cost to the cost for going from 5 to the final stage. So again, that will be solved recursively. Similarly, we need to find the cost of going from node number 6 in the next stage to the final node. Again, that will be solved recursively. Similarly, we will have to find the cost of selecting node number 7 in this particular stage to go to the last node in the final stage. So that is what that recurrence basically means. The cost of selecting a particular node j in stage I is can be obtained by taking the minimum of sum of the edge from that node j to a node in the next stage, okay, plus the cost that will incur in selecting that next node in the next stage for going to the final node in the last stage. Let's suppose the same recurrence can be illustrated here. So if we choose node number 1 in the first stage, so cost of 1 comma 1, meaning cost of choosing node number 1 from the first stage, is equal to the minimum of either choosing node number 2 in the next stage plus the cost that is incurred from choosing 2 later on, minimum of this, and 1 plus, which is the cost of the edge from 1 to 3, plus the cost of going from 3 to the last node, and the minimum of all that, 5, which is basically the cost of edge from 1 to 4 plus the cost of going from node number 4 to the last stage. So at stage 1 we have to make 3 choices. We have 3 choices and we need to select the minimum of the 3. So either we select node number 2 or select node number 3 or select node number 4. Okay. So we also need to incorporate the cost of edge from going from stage number 1 to stage number 2, meaning from node number 1 to node number 2 or to 3 or to 4. Okay. So similarly, the cost of going of selecting node number 2 in stage number 2 would simply be the minimum of 2 plus the cost of going from 5, node number 5 to the last stage. Why is that? Because the cost of edge 2 to 5 is 2, plus would be the cost of selecting 5 in the next stage to go to the last stage. Okay, so it will be the minimum of this 2 to 5 and 2 to 7 because there are only 2 edges from 2 to the next stage. So this is how our recurrence will be created or solved one after another. Now this the earlier example that I just showed you would be following the top-down approach. we'll try to find a formulation for this problem using a bottom-up approach. We'll see how we go about it. Now we can observe that the cost of selecting node number j in the last but one stage. If you see in our example, our last but one stage is V4. In this stage, we have two nodes, node number 8 and node number 9. Now the cost of selecting, let's suppose, node number 8 in the last stage to go to the final node T is simply the cost of edge 8 to 10. There is no decision to be made. It is simply the cost of the edge 8 to 10, as I told you earlier. Similarly, the cost of, for example, selecting node number 9 is simply the cost of the edge 9 to 10. Now, if there is no edge, let's suppose there was not an edge from 9 to 9 to 10, then the cost of selecting node number 9 would have been infinity. That is what is illustrated by the first two statements. Cost of k minus 1 comma j will be equal to the cost of the edge j comma t if j comma t belongs to the to E. It means if there is an edge. If it is not, then the cost would be simply be infinity. Now we may solve using a bottom-up approach the previous equation, the previous recurrence that we just mentioned over there, for cost of 1 comma 1 or cost of 1 comma s. What that basically means is cost of going from stage number 1 by choosing node number 1. Okay, or cost of going from stage number 1 by choosing node source. Okay, by first computing cost of k minus 2 comma j for all j belonging to V of k minus 1. Similarly, then we will try to find the cost of k minus 3 comma j for all j belonging to k minus 3, and so on, and finally we will reach cost of 1 comma s. So we'll be trying to follow a bottom-up approach to solve this particular problem using dynamic formulation, dynamic programming formulation. Now we have maintained two matrices here, or two arrays, two-dimensional arrays here. One is cost and another one is path. I'll later on tell you how we'll use this path matrix or this path array to find the final actual solution, means the path from going to source to destination. But for the time being, we'll mainly be concerned with the cost array here, which will help us to estimate the final minimal cost. Now the values here or for the cost array, the rows represent the different stages and the columns represent the nodes. Okay, same applies for the path as well. Okay, the values that we have filled in there are the base cases. For example, we know the cost of selecting node number 10 in the last stage to go to node number 10 in the last stage, or to go to the sink, is 0. Okay, now if we move one step back, as you can see in this example there, the cost of going from node number 8 to node number 10, or from stage k minus 1 to node number 10, is 2 for both 8 and 9. So we have saved these base cases, and using bottom-up approach we'll try to fill in the values at the those cells marked as infinity. So initially we are setting them equal to infinity. We'll later on see. Similarly, for the path array, what we have done is we have stored nodes values for nodes 8 and 9, that is for stage 4 only. Others we have yet to decide. What the path array, the last row, basically means is that when we are at stage 4, if we choose node number 8, to reach to the final stage we have to go to 10. Similarly, for 9 as well, if we have chosen node number 9 in stage 4, in order to go to the final node T, we have to choose node number 10, and this node number 10 is itself the final node. So we'll illustrate using dynamic programming how we will fill these different arrays. So obviously k minus 2, k in our case is 5, k minus 2 will be 3, so we will start from stage number 3. In stage number 3 we have 3 nodes, one is 5, another is 6, and then 7. So let's select node number 5 first. the cost of selecting node number 5 in stage number 3 is simply equal to the minimum of 6 plus cost of selecting node number 8 in stage number 4 and 1 plus cost of selecting node number 9 in stage number 4. Now this 6 and 1 are the cost of the edges from 5 to 8 and 5 to 9, okay, respectively. So when we find this the minimum, we get 3, okay, by selecting node number 9. So the simplest solution would be, if we are at stage number 3 and we have to decide, and we have selected node number 5, which another node in the next stage should we select. From this computation, we find that if we have selected node number 5 in stage number 3, then the best way to reach the final node would be 9, because that gives us the minimum cost. So we'll store this cost, this 3, in our cost array for node number 5 in stage number 3. So we have stored 3, and we'll also store the node that we use to make this decision in the path array. So we have stored 9 for stage number 3 and node number 5. Now similarly, we have to we'll make a decision for node number 6 in the same stage. Okay, so for node number 6, we can see the cost of selecting node number 6 in this stage 3 is minimum of 2 plus cost of selecting node number 8 in the next stage and 8 plus cost of selecting 9 in the next stage. Now it boils down that the minimum is by choosing node number 8 in the next stage if we have chosen node number 6 in the third stage. So in the cost array, for node number 6 in stage number 3, we will store 4, which is the minimum cost that can be obtained, and we'll also store node number 8 in the path array. That is, for stage number 3, if we choose node number 6, okay, in order to reach the final destination, we will have to choose node number 8 in the next stage, in stage number 4. Similarly, we will find out that for node number 7 in stage number 3, the simplest the lowest cost possible is 4. If you observe, we have only one edge for node number 7 leading to the next stage, and that is from 7 to 8, and the cost of that edge is 2, okay, and plus the cost of selecting node number 8 in the next stage is also 2, so it would add to 4, and we'll also store the value in the path, the node in the path array. Now we are done with stage number 3. We'll go back one step to stage number 2 and try to find solutions or the minimal cost for that particular stage. So we are at stage number 2, and there are 3 nodes in this stage, that is 2, 3 and 4. So we'll take up 2 first. Now the cost of selecting node number 2 in stage number 2 is given by what is mentioned or specified in the slide. If you solve it, we'll see that the best way to go from node number 2 in the stage number 2 to the final destination would be to choose node number 5 in the next stage. Okay, so that is what we will do. The cost of that particular choice or that path is 5. We'll store that in cost array for node number 2, stage number 2, and we'll also store node number 5 in the path array for node number 2, stage number 2. Now selecting the next node, the third node number 3 in stage number 2, we see that there are 3 choices to be available. So either we can go from 3 to 5 or 3 to 6 or 3 to 7, but we have to choose the minimum, okay, considering the cost of the edge as well as the cost of from that particular node. So when calculating the values, we find that from node number 3, the best choice is to select node number 5 in the next stage. We are at stage number 2 and we have to choose a node in stage number 3. In stage number 2, we have chosen node number 3 and we need to decide which another node in the next stage, meaning the third stage, we have to choose. So if we have chosen 3, the best cost would be to select the best would the minimum cost is obtained by selecting node number 4, and the cost of selecting node number 4 is 4. So we store this 4 for node number 2 in node number 3 in stage number 2, and we also store node number 5 for stage number 2, node number 3 in the path array as well. And we keep on following the same for selecting node number 4 in stage number 2. For selecting node number 4 in stage number 2, we have the cost equal to 6 by choosing node number 5 again. And finally, we have reached the first stage. Okay. Now the cost of selecting node number 1 in stage number 1. Okay. In order to do that, we have 3 choices again, either to go to 2 in the next stage, or to 3 in the next stage, or to 4 in the next stage. So again, we try to find the minimum cost by solving this equation here. We find that the cheapest one, or the cheapest node from node number 1 in stage number 1 is to select node number 3 in the next stage. And we store this value, the cost of 6, for in the cost array for node number 1, and we also store 3 in the path array for node number 1 in stage number 1. If the given problem does not require us to generate the path, final path, if it requires only to provide with the cost of the minimal cost of the path, if it does not require the path itself, then we can simply omit this maintaining this array path. But if it requires both the value of the minimal cost as well as the path itself, then we need to maintain this array as well. And how can we use it to regenerate the path? If you have a look at this path array, for stage number 1, you can observe we have chosen for stage number 1 and node number 1, we have chosen the next node in the path to be node number 3. That is what we have just entered here. So we have chosen node number 3 to be the next node in the path if we already have selected node number 1 in stage number 1 to be the first node. Now, from node number 3, we need to find which is the next node in the path. So we go to the stage number 2 and find the entry for node number 3, and the value that we have entered for stage number 2, node number 3 here is 5. So the next node in the path is 5. So first the node in the path is 1, the second node is 3, and the third node is 5. Now, in order to find the next node in the path, we go to the next stage, meaning the stage number 3, and we find the entry for node number 5. Okay, and if we see look at the path matrix, we see that we have entered 9 for that particular node. So our path becomes node number 1 in the first stage, node number 3 in the second stage, node number 5 in the third stage, and node number 9 in the fourth stage. Now, in the fifth stage, we need to choose the node in the path. So we look at the entry for stage number 4 and node number 9, which was the last node in the path, and we find out that we have entered 10 for that, which is also the last node in the path. And this way we can finally find out the actual path itself, and the cost of this path will finally be stored in cost of 1, 1, meaning cost of selecting node number 1 in stage number 1 to go to the final node T. Okay, so we can regenerate all this information easily if we have maintained these arrays. Now we can also have a look at an implementation of the same solution. So this is an algorithm implementing what we just discussed in the previous slide. Okay, the important thing to note here is that we have not maintained a path array in this algorithm. That you can do yourself. You can find out the location where you need to maintain the entries or make the entries in the path array. You simply need to add an array path of I, j. Okay, and what you need to do is you need to find the location wherein you can save in those entries, and then use those entries later to regenerate the path, as I just illustrated in the previous slide. Now, this algorithm is self-explanatory. Okay, this contains all the statements that I just explained in the previous slide, wherein we were able to maintain or enter values in the cost array and maintain values in the path array as well. Now, an assignment you can consider here would be to find the location for making those path entries. So we'll be continuing dynamic programming for a couple of lectures more, and we'll be discussing some other challenges or some other problems that we can solve using dynamic programming. And till that, goodbye. See you later.